So in chapter 6 we introduced the states of matter, and we saw what distinguishes fluids, which are those that float, and those that adapt their shape to the container, from solids, which are rigid and keep their shape. We also saw how solids, when you apply a force, if it's compressive, then you develop a normal stress or tensile, and then if it's parallel and there's another layer, there is a certain restorative force, and that's why we observe shears instead of just observing the object moving. In the case of fluids, we said that fluids just flow, they adapt to the container, and we saw that this is because the intermolecular forces are not as strong in the solids. In fact, every particle in a fluid can be considered to be in motion, right? So we said in solids, we have everything rigid, right? And in the case of fluids, we have sort of particles kind of free to move, and they're moving and colliding with each other all the time. And in the case of gases, they're free to move, but they're very much distant from each other, so they barely interact with each other, right? So that's what a solid is, that's what it's a liquid, and then this is what it's a gas. And these two are able to flow, and so we call them, of course, fluids, right? Because they can flow, right? That was the idea for liquid, and that's the idea for gas. So in this chapter, we're going to study what are the consequences for the principles that we have studied, when we apply them to fluids. One of the first ideas we have to bear in mind is the idea of equilibrium, and this is essential. It's essential for statics, it's going to be essential for hydrostatics, which is the first thing we're going to be studying about fluids. Hydrostatics is the study of fluids being static. And then we're going to study hydrodynamics, which is fluids being in motion. And in particular, we're going to study what we call laminar flow. We'll get to that, which is just when fluids moving like layers. So the first idea we want to introduce in here, of course, all remember, because we already saw that, is the idea of equilibrium. When do we have equilibrium? Is whenever the sum of the forces is equal to 0. In other words, there is no net force. Whenever there is no net force acting on an object, the object remains in the state of motion. There is no acceleration because net force is 0. If there's no acceleration, there's no change in the velocity, there's no change in the state of motion, velocity is constant. If an object is moving with constant velocity, it keeps that velocity, but if the object is stationary, which is another way of saying 0 velocity, it keeps that velocity constant. In other words, it just remains stationary. And so that's the idea of equilibrium, which is going to be very important. Now we're going to observe how that applies in here. We're going to be using also the idea of density, and also the idea of density, and we're going to be, this is mass divided by volume, and also the idea of pressure, which is of course a force divided by an area. So these concepts, we're going to put them now together to analyze how fluids move. And the first idea we're going to have to bear in mind is that fluids, particles are all the time moving, and this is important. Why? If I have a solid and I apply a force, and let's assume a lateral force, so that will create a shear. The shear only appears if this layer is, of course, in contact with another surface that tries to hold it together, so you have a force of friction here, whereas this doesn't really have that friction, so there's a net force of this layer going this way, and there's a net force going the other way. So what actually eventually happens is that you have deformation, right? So you have this scenario. Now, why do you have deformation? It's because these particles are interacting with each other, and so they're bringing them together, they're holding them together. But what happens in the case of fluids when those forces are not in there? Well, what happens in those cases, whenever you apply a force in that layer, let's imagine that this is a fluid, right? Which actually, fluids typically are going to be ordered, so they're going to be randomly scattered. But imagine, just for the sake of the example, this is like this. If I apply a force here, they're not bounded so strongly. So what happens is that actually the particles move, that layer moves, and so the particles flow. So every time that I have a liquid and I apply a force, I see that the object just moves. It's not in the case of solid where I have restorative force because of the interatomic forces. In the case of fluid, that doesn't happen. And so it's going to be a very important realization to see. This is what makes the fluids precisely that, flowing, right? Because they don't have those forces. When I apply a force, they just move and they just try to equalize the pressures. So that's what we're going to introduce today the idea of pressure for fluids. We're going to also analyze how do we calculate hydrostatic pressure and some of the behaviors of fluids. Why do they behave the way they do in comparison with the more common solids that we are used to see? So from the idea of equilibrium, is worth reminding one thing. We said that equilibrium is whenever there is net force equals to 0. We're not going to introduce torque in here. We're not interested in that. We're just interested in purely translational motion. So let's see what this means. Let's say I have an object and I just let it go. Every object on Earth, we saw this already, it's experiencing always, at the very least, one force, which is weight force. Now, if I make the balance of forces in this scenario, what I'm going to observe is that balance of forces is just the weight, and that's going to be equal to mass times acceleration in the y direction. That weight is of course mg, and the acceleration may, so I'm going to be able to cancel, and then I see y, objects in free fall accelerate with minus g being of course gravitational acceleration, right? So then we observe why this is the minus 10 meters per second, because there is a net force, which is the weight and the object falls. If I just put the object on the table, of course the object is still itself, so it's going to have a weight force. It's on the table. But why does the object do not fall? Why do I do not observe an acceleration vertically being equal to the gravitational force? It is because it's in equilibrium. And so we introduced the idea that there needs to be another force that opposes that one, which of course is the normal force of the table on the object. And so we may make that balance. We observe that as normal force minus weight, that's mass times acceleration in y. And we say the object is not moving vertically, that's equal to 0. That's what we observe, that the total force is 0, because the normal force eventually, balances weight, okay? And so this is the case of, we have a net force, so there's motion, we have no net force, we're in equilibrium, right? That is what we call in equilibrium. But what happens now, let's say, if I just remove the table? If I just take the table away, let's say this is the table, so I just take the table away, I observe then that the object just loses that force, which was the normal force, and now there's pure weight. And of course, when I make the balance of forces, that's going to be equal to the weight. And so now I have a net acceleration, which of course is going to be again minus g. So then important thing here to see, thing to see here is that I have, whenever I have no change in the state of motion, right? Whenever I see that the object is moving with the same velocity, therefore the velocity's change is 0, that means that the acceleration is 0, and of course that means that the force is 0, the net force, right? It is where I'm in equilibrium. So there's no net force, there's no acceleration, there's no change in the state of motion. This is the scenario here. And how do I break the equilibrium? I can break the equilibrium whenever I have a net force. For instance, I just add an extra force. Now maybe I just push the object sideways and then the object is going to slide. So I can break the equilibrium by adding a new force that breaks the condition of equilibrium, but I can also break the equilibrium by removing a force from the system. So there's two ways. Whenever I see a change in the state of motion, certainly I'm not in equilibrium. In statics, we're always interested in finding what are the conditions that fulfill this scenario, right? When you have statics, it's because you are concerned of, or you're interested in describing why objects do not move, right? In kinematics, we describe how objects move. In dynamics, we describe why objects move, which is because there's a force is equal mass times acceleration, Newton's second law, and the first and the third one. In statics, the perspective is how do we make things not to move, right? Because typically when you're an engineer or an architect or something, you're trying to build a structure that remains in place, not that just moves around, typically. There's always exceptions, but you are interested in seeing how do I build this roof and these columns and this and that so the structure doesn't move, because if it moves, it's going to collapse. So that I find the equilibrium, I find the conditions such that all the forces are balancing each other and they cancel. But if a new force acts in because maybe I put a load in the building, then I add a new force, and so that can break the equilibrium. But also it can break the equilibrium if the forces already existing in there, one of those is removed. For instance, if you remove one of the columns. That's why it's important if you are making some remodeling of your house, the architect or someone needs to go there and say, oh, this column actually is carrying load, or this is just static. So you can remove walls that do not carry weight, but certainly you should not remove walls that carry weight, or the house may just collapse. This is the idea of equilibrium. We have a net, we don't have a net force, right? Net force is 0, so we are in equilibrium. We can break the equilibrium by adding forces or by removing forces that were existing in the system. So every time you see a system that is in equilibrium and suddenly stops being in equilibrium, it is because something external is coming, or it's because something that was there now is missing. So just bear this thing in mind, because it's an important subtlety. Do not always expect that something external is added. Sometimes something internal is removed. So this is an idea. Let's go back now to fluids. One of the more convenient ideas in fluids is that of pressure. Remember that the pressure is a force over an area. So let's say I have a fluid, and typically this is easier to see with a gas, right? But basically I have a fluid and I have some particles just moving around, and remember everything is going to be moving, and they're moving randomly, right? In every direction maybe. So let's say I take now inside the box, I take just this layer over here, right? And I analyze, hey, how many of these particles maybe are hitting this wall. So what I calculate is add all the forces of the particles hitting the wall and divide that by the area of that wall. And what do I obtain? The pressure. So the idea of pressure, first approximation for fluids, is going to be that the thermal motion of those particles, in the case of a gas, this is typically all there is, thermal motion, they're hitting the wall, and every time they're hitting the wall, they're imparting a force. Why do we know they're imparting a force? Well, obviously because you have a particle that initially if you make conservation of momentum, you're going to see a particle was initially moving like this, and at the end, the particle is just moving, let's say, the opposite way. So then I have a change in momentum. And the momentum is not conserved, it's different from zero, and I know that the change in momentum is of course an impulse, which is an external force, times the time of interaction. And now of course is what's the external force? Well, that force of course is the force of the wall. Why? Because the particle hits the wall. So action-reaction, Newton's third law. What the particle does on the wall does on the particle. So then I see that every particle hitting the wall is going to be hitting the wall with certain force, and I'm going to divide that by the area. So, and then of course this goes from, let's say, I1 to IN, n being the number of particles that are hitting the wall, okay? And so I observe each one of those is applying a force, and I distribute that over the area, then I experience a pressure. Now, how do I reduce this pressure? This is an important idea for vacuum, which will be important later. How do I reduce this pressure? There's typically three ways in which we can see we can reduce the pressure. One, to reduce the pressure, let's say that we want to reduce P, which is pressure, okay? Not momentum, that's lowercase p, this is uppercase p. So maybe let's do this. Right? Why pressure? Okay, the first way is I can reduce this number if I make this number larger. So I can increase the volume. If I increase the volume, it's another way of increasing the area. So if I have a container with certain gas and I increase the volume, then the area increases, and so the pressure drops. And way of seeing this, of course, there's many subtleties here, but just so we understand with the concept that you already have from chemistry and physics that you might have studied before. But if you remember, for ideal gases, pressure times volume is constant. So I'm saying now if I increase the volume, this increases, so this needs to decrease. So if this increases, this needs to decrease, such as the product is constant. So that's something that we understand. How do I reduce the volume in the pressure, in a container? I can increase its volume. Also, that's why if you pressurize a balloon, the balloon increases the volume, so just to homogenize and find a new balance, but we get to that at the right time. The other option is just to reduce that force. So how do we reduce the force? Well, we can reduce force by reducing the velocity of those particles. It's not the same if a particle hits like this than if a particle hits like that, right? The amount of force is going to be also different because you need to change some different amount of momentum. Again, remember the impulse, which is the force, is the one responsible for changing the momentum. So if I go faster, if I go slower, I'm going to change a different amount of momentum when I'm going here or going backwards. So I can reduce that velocity. We will see in thermodynamics that that's actually the idea of temperature, because temperature is the kinetic motion of the particles. So if you remember again, ideal law, that's going to be also constant, right? So if I reduce the temperature, what happens to the pressure? Well, the pressure also needs to reduce, so such as the division ratio is constant. And there's the last idea here, which is the one where I want to get to, which is you can increase the volume so the area increases so the pressure drops, which you have a larger area with the same amount of molecules hitting with the same force. You can make the molecules to go slower, but you can also reduce the force by reducing the amount of material. And we can call that N, and so we remember then that P divided by N, it's equal to constant. And of course you remember this from Gay-Lussac's and Boyle's law and Avogadro. Well, this is, I don't think that's Avogadro, but anyway, an adaptation, let's say. And then we have a pressure over the number of moles. That's the number of moles in P, V times E is equal to INRT, right? So the number of moles, if I reduce the amount of material, then I have less and less particles hitting the wall. So instead of going from 1 to 100, maybe I go from 1 to 50. So how do I reduce? If I reduce the amount of material, of course the pressure also reduces for the ratio to be constant. But here's the idea. What am I doing in that case is actually removing material. So what is actually a vacuum? A vacuum is the situation where we are approaching a scenario where we don't have almost any material. An ideal vacuum will be no material. And because we don't have any more particles, then let's say we go to a box that only has one particle, to the box that has no particle at all. And now I ask you, how many particles are hitting the wall? None. So how much is the force? 0. So how much is the pressure? that pressure will be 0. But this is also an important thing to know in here, right? The pressure here will be lower in here. Let's say this was 1 Pascal, this will be 0.5 Pascals and 0 Pascals or whatever, right? The idea is we are dropping the pressure by removing material from the container. And so that's the idea for a vacuum, is that we don't have, ideal vacuum is that we don't have any particles in there. So they're not hitting the wall anymore. So then we don't have any more force. And if we don't have any more force, this goes to 0, so the pressure is 0. So how do we create vacuum? By removing material. But this is very important. What is the minimum pressure that we can have is when we remove all the material and the pressure becomes 0, but not negative. And that's going to be very important, because whenever we analyze, for instance, the idea of the barometers and the manometers and basically any other scenario where we're trying to say, no, for instance, I'm drinking with a straw soda, and I'm saying, no, I'm sucking the liquid. In fact, you're not really sucking the liquid, because you cannot generate the negative pressure. The best that you can do is generate a vacuum. What's going to happen is that you're going to have a misbalance of forces. You're going to have a net force, which in that case is going to be atmosphere and pushing in, and no force pushing back. And that's going to create a net force in the direction of your mouth, and that's why the liquid flows into your mouth. It's not because you're sucking it, it's because the atmosphere is pushing the liquid up. We'll see that at the right time. But just an idea here of pressure is related to this, hitting the particles, hitting the container. Whenever we remove the particles, we actually generate a vacuum, because there's no more particles hitting the wall. Let's go back now to the ideas of pressure, but now the hydrostatic pressure. Why? Because in the case of gases, gases are very low density, so they actually don't have a lot of weight, although they do anyways. But there's a second idea of force. This is pressure is because of the thermal motion, if you want Brownian motion, or the motion of the particles inside the box. But there's another source of pressure, which is whenever you have the weight of the liquid or the fluid, excuse me, acting upon it. Let's see more carefully. So we're saying that pressure is a force over an area. We have already established that fluids are constantly moving. And now there's a last thing that we need to do before we observe the two conditions that are going to be allowing us to define the rest of the physics of fluids. And this is the idea that if I have a solid block of material, right, let's say, and I just stand under the block, and this is me laying, I'm going to feel some force pushing on me. Actually, I'm going to feel a pressure. That pressure is going to be what? Well, if I analyze the block has certain weight. So that weight is pushing down, is pushing on the area of my body, and therefore it's going to generate the pressure. So this is for the case of a solid. But there's nothing that prevents me from saying, hey, instead of taking this to be a solid, let's take this to be a liquid. That's mass times g. And if I take this to be a liquid, right, then I'm saying how much is the volume, how much is the mass that is pushing me. And as we have said, working in fluids with mass is very inconvenient, practically inconvenient. And so we, instead of using masses, now I'm going to have a column, the same amount of, let's say, now this being this is still the same, this is a block, but now let's imagine there's a column, and that column is from a fluid, right? So to say, okay, so let's say this is a fluid. And so the case is, do I feel any pressure? And you do, of course, feel that pressure. You're going to feel the weight of that column of fluid. And what's the weight of that column? mg. But m is very inconvenient. So something that we do is replace m, or let's do it from here maybe. M is the same as density times volume. So now I can replace and write density volume times g. So now I find an expression for the weight in the case of a fluid, which is more convenient because it depends only on the density of the fluid, which again is an intrinsic property of the material, and of course the environment as well, but basically pretty much from the material, and then the volume, which is how much it's occupying, right? And then times g, which is the constant of gravitation. So from here we're going to observe something at first. It's like, if I take this box, let's maybe go over here. What's the volume of that box, right? That box has a certain area. That area, let's call that A. And it also has certain thickness, which let's call that D, or let's call that H, the height of the box, right? And so I can observe that, of course, the volume is going to be that area times the height, right? So how much do I experience? I'm experiencing a force, which is equal to rho, and then instead of V, I can write A times H times E. And then if I take this A and I divide, I have force divided by the area. That's equal to rho GH. But what's force over an area? That's a pressure. So what do I observe is that every liquid is experiencing a force, which is its own weight, acting on an area, whatever area I'm considering, that's the one generating the pressure. So I have hydrostatic pressure, which is basically the weight of the column of fluid acting on an area. And that is just depending on the height of the object. So let's analyze this with a little more care. This equation depends only on rho, which is the density, depends on g, and depends on h. If you are in the same planet, g will be always the same, considering you're in the same height. If you are talking about the same fluid is going to always have the same density. So what's the only parameter that matters for pressure in this case is the height. And that's an important thing to realize. If I have a beaker like this, and I have a beaker like this, and both have the same amount of liquid, and I'm observing a point here, and a point here, and I ask which one is experiencing higher pressure. Well, I just need to see that the pressure here is the result of this entire column pushing down, right? So what matters here is the height here. And this one is going to be this column acting here, and that's also height h. So this and this point experience the same pressure, because hydrostatic pressure only depends in the depth. It's irrelevant how much volume of water is in total, because the only volume that's acting on me in this point is the volume that's in contact with me. And that's just defined by how much height is in there. So this might be something a little bit counterintuitive first, but everything we did here is obviously understandable. You follow and you agree, therefore the conclusion needs to be followed. The problem here is that when we say our intuition says, oh, this doesn't sound right, it's just simply because our intuition is badly trained. That's why we have to make the intellectual effort of making science. Once we come mathematically and rigorously come to this definition, we have to accept this definition because this is the conclusion of the argument. So of course, let's get used to remember and think that the pressure depends only in the fluid, depends only on the height of the column. So if I put my head under the sink, let's say the kitchen or the bathroom sink, and I feel it, and I put my head 10 centimeters in, it's going to be the same pressure that if I put my head 10 centimeters in the bathtub, if I go to a swimming pool, or if I go to the largest ocean on Earth, and I put my head 10 centimeters in. How much water there is, it's irrelevant. The only thing that matters is what's the distance from the column, from the surface of the liquid all the way down. That's the idea for hydrostatic pressure. Let's just see another idea, which will be the case of what is the hydrostatic pressure but for atmosphere. So in the case of the atmosphere, we're gonna be just on Earth, and I'm just standing on the ground. I can describe that because there's an atmosphere, I have an entire column of air above my head. And so the question is, how much is the pressure that I feel at this point? Well, the pressure is gonna be due to all that weight acting upon me. So that pressure, of course, is what we call the atmospheric pressure. We can just call that P sub 0 because it's sort of like a reference point, like the initial, so to speak, because every time we are on Earth, we are certainly experiencing them, which is the atmospheric pressure, and that's called 1 atmosphere. That one also we can write in pascals as 10 to the 5 pascals, and we will introduce also, it's not relevant, but we will see how this is actually also described as 760 millimeters of mercury, okay? It's another unit. We'll get to this in a second. Let's just see, before we go for that, another idea. Let's say that you are under because the problem here is that atmospheric pressure with gases do not have a well-defined, sometimes a well-defined density. Certainly there's no well-defined density. There's many different layers in the atmosphere and blah, blah, blah. But we can calculate that, take that as a background, so to speak, and assume that's 1 atmosphere. What happens now if I'm just on a swimming pool and I'm just down here, right? What do I observe now? Well, I certainly observe the hydrostatic pressure, and that pressure is going to be given by the density of the fluid times g times the height or the depth of the water, but I'm also going to be experiencing all this column of air, which is the atmosphere, pushing down, right? So what we typically define is the absolute pressure, if you want. This is the absolute pressure is given by the atmospheric pressure plus whatever pressure you have, which we can call P if you want, which of course is atmospheric pressure plus rho GH. This pressure over here sometimes is called gauge pressure. Because every measurement that we do on Earth has always the background of atmosphere, we can't just remove that, not always add the atmospheric pressure and then just simply refer to the pressure, the hydrostatic pressure due to the depth. And so if I'm making, if I'm diving, because the atmospheric pressure is always the same pressure, about the same pressure, my measurements always with reference to the atmosphere are going to be perfectly defined by this material. I would only, if I actually was interested in the absolute pressure, I would only have to add this value here. This is just an idea of why gauge pressure, you might see it in there, and sometimes gauge pressure is just simply the absolute pressure minus the background of the atmospheric pressure. Whenever you have higher pressures than atmosphere, sometimes you have a little more than one atmosphere, sometimes you have a little bit less. That's very much studied in environmental sciences, and that's, you can see it in meteorology. That's constantly studied. We see some problems actually about some ideas like this later in fluid dynamics for hurricanes. But just another idea. Now, why is 760 millimeters of mercury? So Torricelli was one of the disciples of Galileo, and they started because they started working with the idea of no friction. No friction meant there's no air, no nothing. And then they started to say, how can we create this thing that we call a vacuum, right? And of course, they didn't have the idea of molecular physics that we have. That's sort of an anachronism because we're just bringing the ideas of modern into the old time to understand, but they of course didn't have those ideas, so they had to explain it anyways. So one of the experiments that Torricelli made of creating vacuums and vacuum pumps and all these things that were being developed in the 17th century and onwards is the idea of just taking a column of mercury, right? Fill it to the brim, let's say, right, with mercury. Let's say this is mercury, and now take a ball also with mercury. Let's say a ball with mercury. Right? This is also mercury. And what he did is just take the cap, put your finger or something, invert it, and submerge it into the ball, right? And so what you're observing now, let's take the ball, and that was the original level. And so what he observed, and you can observe yourself, I don't think you can with mercury because it's very, usually it's poisonous, depends on the particular. But that's actually, I think, forbidden. But anyway, you can have mercury, and you're going to observe that the column of mercury drops a little bit. So this is going to be mercury, and all of this is mercury, and the level maybe raises a little bit. And that's the ball, right? And then you say, why does the entire volume doesn't drop? Because if I take this mercury, I put the cap, I reverse it, and I empty, I see the mercury flow. But whenever I take the mercury, I put it inside the ball, and I empty it, it drops a little bit, maybe it stays there. And so I'm saying, hey, why does this thing fall? I know for a fact that this thing is pushing down because it has a certain amount of pressure because it's the own weight of the column. But this thing is not pushing down. And so I remember every time there's a force, but there's no motion, there needs to be another force that balances that. You remember the idea with the table. I have the object has weight, but whenever I put the table, the object doesn't move. Therefore, there's a normal force counterbalancing this. What other force is counterbalancing this thing? And that is the idea of the atmospheric pressure. Because this ball is an atmosphere, this ball has columns of air acting on the fluid. So there is weight of atmosphere pushing down the volume, the liquid, which is going to try to go up in the column. And at the same time, you have the column, which has a weight pushing down on the other liquid, trying to overflow it. If we were in vacuum, the entire thing would just drop and just fall. But because we have an atmosphere, right, we're pushing it down. And this over here, of course, is going to be the vacuum, that area over there. And so how much is that height? Well, that height, it turns out to be 76 centimeters, or that height is actually about 760 millimeters. So that's why they say that one atmosphere is 760 millimeters of mercury, because if I take a column of mercury and I turn it upside down inside of mercury, and I just observe that the mercury is pushing, but mercury is pushing on mercury, the atmosphere is pushing, we have a force of atmosphere that goes down and then transfers inside, and a force that goes from the mercury pushing down. And they balance each other, they find an equilibrium. Where do you find the equilibrium? Whenever the weight, which is responsible for this, the gauge pressure, is such that you have 760 millimeters of height. That weight is balanced with the weight of the entire column of air pushing down on the ball. And that's the idea of 760 millimeters of mercury. If we use waters, and we will see this in a problem in the solving problems, if you were using water, you will see that this is 10 meters. So 10 meters because of the density change, right? 10 meters of water are equivalent, say, to the pressure of atmosphere, which another way is saying every time that you dive 10 meters down, you gain 1 atmosphere. So 10 meters under the surface of the water, you have 1 atmosphere. 20 meters, 2 atmospheres, 30 meters, 3 atmospheres. And if you're trying to go up, you're going to have to do the same. Every time you want to pump the water 10 meters, you have to add 1 atmosphere of pressure to lift it, right? That's going to be, excuse me, the idea over here. Again, you can always add the atmospheric pressure, but atmospheric pressure you're going to feel regardless, right? So inside the liquid and water, that will be 10. Other liquids with other densities are going to have different values. Liquids that have lower density than water are going to have a larger depth before you recover that, because density is multiplying. Liquids that have a higher density are going to have a larger pressure for the same height. Basically, this is the idea. Let's just introduce the two ideas, the last two ideas, and Pascal principle, and solve some problems. Let's say now I have a fluid in a column, like a cylinder or something, and this is filled with fluid, okay? And it's standing on the ground. And I'm asking you, is the fluid moving? And you say the fluid is not moving, it just stays in there, right? There's some fluid in here. Okay. What happens, let's say it's water, if you want to imagine just that, say this is water. What happens if I make a small hole over here? What do I observe? What I observe is the liquid starts leaving from there, right? And then it will just drop something like that. And so I'm saying, why is this the case? This liquid was in equilibrium, it was stationary, and suddenly it starts moving. Am I adding any extra force? And the answer is no, you're not adding a force, in fact you're removing one of the forces. And this is two observations that we can make. From here we can make two observations that are very important to understand fluids. From those then we can go to Pascal's principle, which is good for applications in lift and hydraulic presses and so forth. Why does this thing move here? Remember, fluids are moving randomly in every direction. So all the time are hitting the wall because of thermal motion, right? If I remove the wall, the particle that comes through here doesn't have anymore another force on the wall to go back. So it's going to be able to leave. So why this falls in the case of gas is just simply a matter of pressure. In the case of liquids, on top of the thermal motion, we also have the hydrostatic pressure, which again is just given by rho GH. So there's two effects in here, is that all this amount of liquid, if you wish, or all this for this particular atom, is pushing down on this one. And that's also going to make it leave. What do you observe? And we'll go that to Bernoulli when you cut the hole here or there. We're going to see that there's a different pressure because there's a different height, and that's going to be transferred or translated into a different velocity leaving this bucket, right? We'll see that in Torricelli theorem extracted from Bernoulli's at a different time. So why is this happening? Is because I'm breaking the equilibrium. So one thing I can see is that the wall is acting on that thing. And what is the net component of the wall? Well, actually, let's start from something else. We have the particles moving in every direction. One of the first observations we're going to make. Let's maybe enunciate the, actually, yes. Let's enunciate the conditions. The first thing that we can observe about liquids is that the fluid carries the pressure in every direction. Right? The fluid carries the pressure in every direction. In all directions, the same. The second observation is that the fluid exerts a force or perpendicular to the wall. Let's observe these two ones in a little bit more detail. This one is going to be much easier to see, but let's start with the first one. Why does the fluid applies the pressure in every direction? Important thing. You have particles moving randomly. So at a given time, that particle is going to be experience a force of another particle that comes and hits here, another force that's moving and hits in there, another force that hits and moving there, another one that maybe another particle is coming here and hits it. And because they're randomly moving, the net force acting on this is going to be zero. It's in equilibrium, right? That's the condition. But then action-reaction, what this particle does to this, the particle does on the other one, right? What this does to this does to that. What this does to this does to that, and so forth. And so you can see that actually this particle is exerting a force equal in every point in space. And that's going to be very important. And this is something that we observe ourselves. Because the force, of course, is the same, the pressure is always going to be the same. The pressure for a given point in a liquid is the same in every direction. If you are underwater, and typically your faces or your head is not that large, so if you are, let's say, putting your head like that, you feel the pressure in this ear, which is going to be the same if you go like this, if you turn around, or if you go up and down. Upside down and upside down, I don't think you're going to have a pressure difference of more than 1%, and I don't think your ear is going to be capable of distinguishing that. But basically, or you could estimate how much is the difference. But the idea is you don't observe a difference in direction with the pressure, right? Your ears feel the same whether you're pointing up, down, or whatever, at the same height. Again, at the same height, because the only thing that matters is the height of the object. So if I take a column of liquid, a point here feels the same pressure like this, like this, like this, and like this. And a point here feels the pressure like this, like that, and like that. And again, because it feels the same pressure, so it's applying the same pressure to the other way, to the other, in the opposite directions, right? Action, reaction. So this is the first idea. Fluids transmit their force in every direction, and they have the same pressure in the same. Why is in every direction? Why is this important? Because if I now apply a force, and we will see that in Pascal, and I'm assuming the fluid is incompressible, if I apply a force, I'm going to have a net extra force. So I'm breaking the equilibrium. So that force is going to be extra one pushing down, which is going to make this molecule push the next one, which is going to make the one pushing down and pushing down and pushing down. So that one is going to be transmitted vertically, right? And so I'm going to be able to use fluids to transmit forces or transmit pressures. The other idea is why this works if I am actually having a column of water, let's say, and we'll see this again, and I have a piston here, and I make a fluid here, I put fluid, I have another piston. What happens when I push down here? I see this thing going up. Why does it go up? Because the pressure I apply is transmitted vertically, but it's also transmitted in the other direction, because the pressure in this point is going to be the same in every direction. It transmits, that's the idea of fluids, it transmits the force in every direction. And that's because of the random motion of the particles. Now, if you have paid attention, this is a subtlety, but anyway, if you have been paying attention, we have built the entire thing saying motion into directions is independent. So you can treat as vertical, doesn't talk to horizontal. And now I'm telling you that the vertical force is transmitted to horizontal. What is going on in here? Well, in reality, that's a little bit of a subtlety, but particles are not colliding. They're not point particles, they're not colliding front to front. They have what in physics we call cross-section. And so in fact, the particles are more like this, a ball, and they're not completely aligned. So even if I apply a force here, this force is going to hit this ball over here. So what's going to happen with this force? It's going to go there, right? If I take tubular poles and you hit like that one just goes in diagonal. So this is how I transmit the force vertical into the horizontal. So they're not perfectly arranged in vertical, and so I don't apply a force and it just goes purely vertical as it would happen, because they're not perfectly and they have a certain cross-section, or they have certain size. When they hit each other, they go that way. So you can make this analogy, like imagine at the beginning of a pool or a billiard game, you put all the balls in there, you just hit it. Even if you hit it frontal, you're going to see some balls going sideways. That's because the balls have size, and so they're not hitting front to front. They're not perfectly frontal collision. They're not perfectly in one direction, right? So it's just the subtle thing is you get, oh, wait, what's going on here? It's accounted for. But basically, for us, for our purposes, the force is going to be acting here. The pressure is going to be distributed all over the liquid. That's going to be the foundation for Pascal principle that says the in fluid forces is transmitted in every direction. The second idea here is just to say that the force exerted on the wall is always perpendicular to the wall. And why is that? Let's say that I had a force of a particle hitting the wall and had certain parallel component. If I have a parallel component, and by the way, this is for stationary fluids, or static fluids, that's why we say hydrostatics, because we're studying fluids stationary. So when the atom is hitting the wall, if it had certain parallel component, right, let's say that the atom was like maybe going like this and hitting the wall. One way of saying this is that all the particles randomly interacting, one is going to go down, but one is going to go up, so at the end the forces cancel in the vertical component, in the parallel component, and the only one you have a net perpendicular. But another way of saying that is if I, instead of taking a particle, I just take amount of volume in here of fluid, and I say what force is that fluid making in there. If this fluid was making a force which goes parallel to the wall, what the fluid does to the wall does to the fluid. So the fluid will feel a net force going in the direction of the wall, and so the fluid will be in motion. But the assumption is that we're studying motion stationary, and I don't see a glass with water is not moving. If I observe a certain amount of volume there, it's not just moving around, it's just in there. Well, the molecules, again, the molecules are swerving around, but that amount of fluid is not. So then what do I conclude from that is that indeed the force is purely perpendicular. There cannot be a net parallel force. If there was a net parallel force, then the thing would be moving sideways, and it's not. So the two ideas in here, fluids are always carrying the pressure all over the fluid in every direction with the same pressure in the same height, okay? The pressure is determined by height. But if I add an external force, once I put all the liquid, I have an equilibrium. So for a given height, all the forces are balanced. For a different depth, the forces are going to be different, but are still balanced within that level. When I add an extra one, I have an extra one in this layer that transmits to this one, to this one, to this one, and then it's also going to be transmitted sideways, and sideways to the wall, sideways also to the other one. So if I push down here, this pushes down, pushes to the sides, pushes up, which is, again, if we go back to the idea of the barometer of Mercury, when he puts the column on the ball, right, the atmosphere is pushing down the mercury is going to be bringing the force up, which is going to be the force of the atmosphere. And then the liquid is going to be pushing down, which is the weight of the, if you want the center of mass, it doesn't matter, the volume of the force of the mercury down. And when these two cancel, net force is 0, no motion, now I have an equilibrium. So why does the column fall but just falls a little? It falls enough so I have to adjust that the weight of the column is the same as the weight of the atmosphere pushing it up. Now we see that liquids are capable of transmitting motion. And this is very important from an applications point of view. This was seen by Blaise Pascal 1600s. Why is this important? Because now I can use this to my advantage to build what we call hydraulic presses. Let's see an example. Let's see the theory about this and what we mathematically can do with this, and then some problems. So last thing that we're going to see is Pascal principle. And the idea here is, of course, let's say I have a column of, or some liquid in a container like this, where this arm has an area A2, and this one has an area A1. And this is an equilibrium with a fluid, right? It's filled with a fluid, it's an equilibrium. Okay, so what's the next thing that we observe? We apply a force in here, which we call F1. What do we observe? What do we observe? Let's make that the column is larger, right? And let's say that this is, I'm applying a force down here on this area. What do I observe? Well, I expect that as I push down, this one goes up. And why? Because the fluid is going to carry on the force. So the force of this is going to be transmitted down to the liquid. It's going to go to the liquid. It's going to go also sideways to the wall. But then once it gets here, it's also going to be going sideways. And eventually it's going to be going there. Now, it's important to see that, from the reasoning that we made, that the pressure, the input pressure is going to be the same as the pressure output. Again, assuming incompressible, right? So the input needs to be the same as the output. But what is the force, what is the pressure input? Is going to be the force 1 divided by the area 1. And what's the definition of the pressure here? It's going to be whatever force do you receive divided by the area 2. And what I can do from here, of course, this is basically an equation of balance, but what I can do over here is saying how much force 2 do I extract from an input 1 is going to be equal to the ratio of the areas. And if you want, actually, just do this. Okay, let's just do this first. Times F1. So the force 2, it's going to be the output force, is going to be the input force multiplied by the ratio of the areas. Let's say that this area is 10 times larger than this one. So what I'm going to have is A2 divided by A1, that's going to be a factor of 10. So if I put 1 Newton, 10 times 1 is going to be 10 Newtons output. If I put 20 Newtons, it's going to be 10 times 20, it's going to be 200 Newtons. So what I have here effectively is a way of multiplying forces. So because I input a force in a smaller thing, I'm going to extract it larger at the other way. And this ratio, which is also the ratio of forces, is what in engineering, but I'm not interested, that's sometimes called mechanical advantage. And now you might be a little bit concerned because they say, wait, can you multiply forces? Well, of course you can, and you've done that all your life. When you're using a pulley system, you're using a pulley system because you are multiplying forces. When you have an inclined plane and you say, I have to pull this thing up vertically, if I go through an inclined plane, I need a lesser of a force because the component of the weight vertical in the direction, of the motion, and it reduces, right? We have seen that all over the place. So the problem here is that we expect forces to be conserved for no reason. What actually needs to be conserved is the energy. And so you can see that if you apply a force here, F1, and F1 is smaller than F2, work needs to be the same. Work is just simply, again, the product of work is the product of a force times a displacement. So if force 1 is small, then delta x1 is going to be large, right? And that needs to be the same as F2, where the force is very large, so the displacement is going to be very small. So if I, let's say I have a ratio 1 to 10, I have 1 Newton here. To move this 1 meter, and we'll see that in the problems, that needs to be 10 meters to have 1 meter here, I need to have 10 meters here. If I have 10, I have 1, because the energy needs to be conserved. So forces can be multiplied, energy cannot. So this is an idea of mechanical advantage. This is a hydraulic press, is one of the machines. You're going to see that the wedge, an axle of and a wheel, an inclining plane, the pulley, etc. Those are examples of simple machines. We haven't studied those. They may be more interesting from engineers. But this is the idea of mechanical advantage. I can multiply forces that help me do some work, right? That is actually at the core of mechanics, because the mechanics again comes from mechanic, from machine. So that's the idea of machines. Machines are helping you to do certain ideas, certain tasks. And so multiplying force is actually very convenient, because now I can just have a car is a ton, but I can just push with my bare hands and I will never be able to lift the car. But if I go with hydraulic press, I can just push. I will just have to go longer pumping to move it higher, because I have to cover a larger distance to conserve energy, but then I'm going to be able to actually lift the car. And so this is the idea of Pascal principle, which is in press. Let's see now some examples, some numerical applications of all these principles. So problem number 1 in discussions is something we touched upon before. It says that there is estimated the pressure needed to raise a column of water to the same height as a 46 meter tall pine tree. So let's imagine there's a pine, and there's a pine which is 46 meters, right? And we're trying to make a column of water reach this much. So we could imagine that, let's say we have a pump here or something, and we're trying to pump that water from a reservoir of water or something, right? And we're trying to pump it up all the way up to 46 meters. And so how much pressure we have? Well, if you remember, it's going to be about 4.6 atmospheres, because about 10 meters is 1 atmosphere, right? But we're going to see exactly how we do that. So the first thing is, of course, remembering the density of water, which is 1,000 kilograms per cubic meter. And we're just going to write that thing somewhere. And the other thing that we know is that we want a height of 46 meters. So what's going to be the pressure field at this point? Well, you have to have at that point enough pressure to sustain the entire column, or the water will never raise there, right? If I'm trying to lift a box and at some point I don't have enough force, I just keep piling up. Imagine this. I'm just here and I'm standing with my hands like that, and I put a book, and then I put the second book, and I put the third book, and I put the fourth book, and so forth. And I'm putting books all the way up to reach 46 meters. Now, at some point, of course, the more books I put, the more weight I'm sustaining. So I need to have a normal force, let's say, enough so to sustain the entire force of all the weight to be able to lift there. If I just don't have enough force, the thing would just collapse and everything would go down. So this is the same thing with the pump. The pump needs to be able to start piling up books of water, if you wish, all the way up to 46. Another way of saying what is the force in there, that's going to be the total weight of all the column. So it's going to be the force in here that the pressure pump needs to make. That pressure pump needs to make a force such as the force, or the pressure in this case, is rho GH. And because water is 1,000, G is 10, and H is 46, that's going to be 46 10 to the 4, or 4.6 10 to the 5 pascals. Now remember that let's write it here, 1 atmosphere, usually better say 1 atmosphere is about 10 to the 5 pascals. So we have 10 to the 5. So how much do we have? We have 4.6 atmospheres, right? So to lift the water all the way up to here, we're going to have 4.6 atmospheres. We wouldn't be able to do this with less than 4.6. We will be able to reach lower. And this is important. If you pressurize the water, that's possible, but you will never be able to make a vacuum such as the thing raises there. A pump that works by creating a vacuum would only be able to lift the water up to 10 meters, because 10 meters, we can see that. If we take, we want to say how much is the column of water when the pressure is 1 atmosphere, right? So let's say if pressure is 1 atmosphere, which is 10 to the 5 pascals, that needs to be equal to rho of water times GH. That's the height that we're trying to solve. So that's going to be the rho of water is 1,000, which is 10 to the 3. That's going to be 10. That's going to be H. So this is going to be 10 to the 4 times H is equal to 10 to the 5, which from here we see that H is equal to 10. So the height of 1 column of water just pushed by atmosphere, if I take a column of water and make a vacuum on the tube, the water, let's say I put this in a bowl, right, with water, and I say, hey, the bowl has water, atmospheric pressure is pushing down. Let's make the bowl like this so it's more obvious, right? This is water, and the atmosphere is pushing down, is lifting up. This also is pushing down. This pushing down pushes for 10 meters, and 10 meters are enough to equate atmospheric pressure. So you have to pressurize the pump basically to lift it up in a building. But it's also an idea where you see power, tower powers, right? We will see that in Bernoulli. We have water towers, because when you have electricity, you can pump up the water there, but in case that you lose electricity or your pump doesn't have enough strength, we can use gravitational force to convert that into pressure, and we will see that allows you to have water even in the absence of electricity, or even with the pump not working that nicely. We'll see that in a later video, but this is just the first idea. How much pressure do you need to lift liquids? Or you have to compensate for pressure. And let's keep that in mind, because all those concepts, kinetic energy and potential energy, we already saw. But we're going to start to see that we need to make forces to have liquids in height. We need to make work, because we're applying a pressure, which is another way of saying a force over over the displacement. Excuse me, over the displacement. So that's going to be, it's in the back of our mind, so when we bring Bernoulli theorem, there's not going to be much of the difficulty. To lift the column of water 46 meters, we're going to have to put enough pressure to sustain the entire weight force on that point. That force is going to be 46 meters times 10 times the density of the liquid. If this was mercury, which is I think 17,000 times, that will be about 17 times more, right? Atmospheres, right, needed, because you need more pressure for more dense liquids. If this was oil or gasoline, that's less dense than water, then you will need less force to actually pump the gasoline. Anyway, the idea here is height of a column has certain weight, hydrostatic pressure. We need to apply that force to keep the thing all the way up. Problem number 3 in discussion says determine the total force and the absolute pressure on the bottom of a swimming pool. Right, the dimensions of the swimming pool are 28 meters, and the width of the swimming pool it's 8.5 meters. The depth of the swimming pool it's 1.8 meters. And they're asking about the total force and the absolute pressure. Now be careful reading the problems. This is very important, just to avoid silly errors. If they ask about gauge pressure, is the pressure just simply with respect to atmosphere, so you don't need to add atmosphere, but because it's absolute pressure, actually you have to account for atmosphere action in the swimming pool. If you're actually testing the material's strength, probably you want to consider total pressure, because that's actually all the forces acting on the object, right? But it depends on the particular scenario. The total force from the outside of the pressure is going to be acting opposite, so it just cancels each other, so you can disregard that one. So again, depends on the application. In this particular problem, they're asking for total pressure or absolute pressure. That's going to be gauge pressure plus atmospheric pressure. So the total or absolute pressure is going to be, of course, atmospheric pressure plus hydrostatic pressure, which is rho GH. And here comes the thing, rho of water is 1,000. We assume the water is 1,000 times 10 times the height, which is 1.8. How much is this? That's 1.8 10 to the 4 Pascal plus 10 to the 5. So the total force is going to be, that's like 0.18, right? This is 0.18. This is 0.18 10 to the 5 pascals, right? So when we add together, this is 1 10 to the 5 plus 0.8 10 to the 5. That's going to be 1.18 10 to the 5 pascals. That's the absolute pressure, right? And then the second thing we need to do is just obviously answer the question that will be A. Answer B is about the force. So if we have pressure, it's a force over an area. So force absolute is going to be the pressure absolute times the area, okay? The area is 28 times 8.5. So if we multiply this, it's going to be 238 square meters. And the product of 238, so the absolute pressure, is going to be the total pressure, which is 118 10 to the 5 times 238, and that's going to be 2.8 10 to the 7 newtons This is the absolute force. So what is the force at the bottom of the pool? This amount of this brick or whatever it has to sustain 2.8 10 to the 5 newtons. By the way, you could divide that by 10 if you want, and then you would have 2.8 10 to the 6 mega newtons, right? A million newtons, which will be like equivalent of having 2.8 tons in kilograms, tons of water in that point acting, or actually the entire weight. So this is, imagine like 2.8 is going to be like a large, actually no, it would be 2.8 million, right? So the question is like, could you put this, or will you put this, obviously not the swimming pool, on an apartment, let's say in a building complex? That wouldn't make like a lot of sense because it's a huge amount of weight. That's why you have to be careful. Like for instance, if you were building a fish tank, a large one in a hotel or something, you have to be extra careful because water seems to be, I just put water like I put, I don't know, like a sofa or something, but this is very dense. This is 1,000 times denser than air. So the entire weight acting on the surface, if you were in the second floor, let's say, that needs to be sustained by the columns, right, of that thing. So this is a dangerous thing. So make your calculations carefully. And of course, usually, I mean, I don't think anyone will put 28 meters a long swimming pool. Maybe if you're a millionaire or something. But you can use the ground floors, all the force goes directly to the ground. But otherwise, you're going to have to carry that weight down, right? So that's why you have to be careful in building a swimming pool. Just make sure that the terrain where you're building it sustains, and if it's in a building, right, in a building apartment complex, that it sustains the weight. We're saying why? Because all the force acting on this layer is going to have to be transferred down through the columns if you're actually designing this house. So that's an important thing. Another conceptual question to end this question that says, what will be the pressure against the side of the pool near the bottom? So basically they're asking us, what is the pressure here, right? We have found the pressure here, and the question is, what's the pressure there? And this is theoretical answer. We already saw that. The pressure at the side is going to be the same as here, the same as here, the same as here, the same as here, the same as any other point at the same height, because pressure only depends on height. And the point of that corner, that precise corner, if we could think about that, that corner is going to have that lateral pressure as well. The pressure needs to be the same, pointing down and pointing to the side. If we take a look at the corner, right, let's go to the corner, we will see that thing. This pressure down is the same as this pressure sideways because it's exactly at the same depth. So your walls of the swimming pool should be able to sustain that pressure, which then if we divide by the area, the force here is going to be much larger than the force there, than the force there, than the force there. So if we actually observe a dam cross-section, you're going to observe that typically you have a dam and you don't just build a wall like this and you say, okay, done, typically, right? Because the force in here goes like this, right? That's the force acting here is the force due to the pressure here, which is much lower than here, which is much lower than here, which is much lower than here. So the down that you go, the higher the force, the lateral force or the normal force that the water is pushing to the side, because again, fluids transfer the pressure in the same in every direction. So how do you solve for this? Of course, this will, if this is like this, the pressure empty like that. So in fact, if you try to build a container and you start putting water, you're going to see it just typically breaks on the bottom because this is the stronger force, because all the liquid pushing here sideways but also down, this contains its own force with all the other things, right? So how do you observe dams to be built? But the dam bridge walls are built like this. Why? Because then now this thing can sustain a much larger force than this one and that one. Right? This is of course an idealization. But this is the idea of the pressure. If you have to, every point in the wall needs to sustain the force acting laterally. Again, it's going to be the maximum tensile or compressive stress of that material at that point. So you have to calculate for all of those. So again, we're going to be connecting concepts of stress and everything now to the ideas of liquids. Because liquids are taking as incompressible in here, they transfer the pressure in every direction, and that also means that to the side is going to be the same pressure that it receives downwards. And if I take a small portion of the area, I say like this tile, that tile has that area, I multiply that pressure at that height for that area, it's going to give me the lateral force, and the lateral force is the same as the downwards one, but also that in a real world application, why does it look like that? Why do we observe dams built this way? Because the deeper that you go, the more weight you're going to have, so the more force laterally it's acting. We saw that like for a standard swimming pool of only 2 meters, this is a huge amount of force. So problem number 5 in discussion says there's water and oil and they do mix are in a tube with the shape of a U. And the tube has oil here, let's say, right, that's oil, and the rest is water. They're called points A and B in the drawing. This column of oil, let's go all the way only up to there. So this column is 27.2 centimeters, and the distance for the water goes all the way up to here, that's a 62 centimeters, right? Okay, so they don't mix together and say they come to an equilibrium as shown in the figure, which we are drawing here. This is oil and the rest is water, okay? And then they say, what is the density of oil? Now, one thing that we can obviously see is that pressure here and here is going to be the same because that's the pressure due to the atmosphere that we're going to call P sub 0, which is 10 to the 5 pascals or 101 kilopascals, something like that. Okay, very good. So that's the pressure due to the atmosphere, which is the column of air above their heads is pushing down on the liquid, okay? And what's happening is that this one also, regardless of that, and now we can, and we will eventually ignore, you will see why, but the idea here is that if they're initially in equilibrium, oil and water, then water is more dense than oil, and so it's going to start pushing it down because it has more weight for the same column. So what's going to happen is it's going to start pushing, and it's going to be pushing up to the way that the column of oil increases in height, so such that the weight of that column matches the force of the weight of of the weight of water. Now it's a very important thing to know, to notice in here to solve. Excuse me. If you try to say what is the pressure in here or in here, let's say because of the column, the problem is that it's going to be in terms of the density of oil, and that takes you nowhere. So something else that we can try instead is just to analyze what is the pressure at a point in the interface. And why at a point in the interface? And this is important. It's obvious that the point here is experiencing the pressure due to the air plus the pressure due to the column of oil, right? So let's take pressure A, and that's the absolute pressure. It's going to be the atmospheric pressure plus the gauge pressure. And that's the hydrostatic pressure due to the oil, which is going to be P sub 0 plus rho of oil, G, and the height of the column of oil that we can describe sub oil, okay? That's fine. But what else do we know about this point? This is the interface between oil and water. The pressure here is due to all this thing pushing it down, right? What about in point in here? Well, a point in there is going to be experiencing all this column of water. All this column of water, which we can call H of water, right? So we're going to say that the point B, we're going to experience the force of the column of air, which you could say it has an extra height, yeah, but it doesn't really affect because atmosphere is huge, so this is negligible in the context. And then we have the column of water, which is going to be the pressure due to the oil, and this is going to be due to the water, and that's going to be the atmospheric pressure plus the height of that column of water, which is going to be rho of water times G and the column of water. Okay, so we know the rho of water is 1,000 kilograms per cubic meter. We actually don't know the one for oil because that's actually what we're trying to solve for. So what do we do with this, right? From here we get the number, we can actually get a number because we can get the numbers here is 22. This is the thing. H of W is the same as H of oil plus, H of oil minus that, 862, correct? Yeah, but you will say, okay, that's all good, but we find the weight in there. So what, right? Well, so what is that? Because this point and this point are at the same height, they have to have the same pressure if the fluid is in equilibrium, and it is, because it's not moving. If this pressure was higher than this one, you would have a net motion here, because this one will not be able to sustain this one, and it will move. And if this was lower than this one, this will be pushing up, and this will be moving up. But we don't observe that because it's in equilibrium. So it's important to notice the necessary, the point A needs to be the same pressure as the point B, because it's in equilibrium. And that's going to be allowing us to solve actually the problem, because PA needs to be PB. Then we're going to find the P sub 0 plus rho oil GH oil, it's equal to P sub 0 plus rho water G and the H of water. But rho 0 and rho 0 are going to cancel, because they can cancel together, and I have this. And so I can find that the rho sub 0 GH is not sub 0 oil, water GH water. Now G's and G's are going to cancel, and so I'm going to find that the rho of oil is going to be equal to the density of water times the height of water divided by the height of oil. And that's going to be 1000 times, and here I'm going to find the height of water, which is the height of oil, 27.2 minus 8.6, which is going to be 18.8, 18.6, and that's going to be 18.6 centimeters. I mean, if you pass to meters, is fine. It's just centimeters and centimeters are going to cancel each other. So if you want to be always consistent, maybe write it all in meters. Okay, let's write 0.86 meters to avoid making errors. So we can just write there 0.186 meters, and that's going to be divided by the height of the column of oil, which is 0.27.6. And that's about actually 60 something. This is a 2. This is about 0.68, so 69, let's say. So 0.69 times 1,000 is going to be 690 kilograms per cubic meter. So how much is the density of oil? 690 kilograms per cubic meter. Now, observations that we can make in here. First of all, do not forget, same fluid in equilibrium, the same height has to have the same pressure. The second thing, in interface, of course, we're having the same fluid, so that's going to be fine. Also, if the oil was less dense, the column will be taller, because the new equilibrium, this will be higher, so it will be just pushing it upwards, and this will be narrower. Of course, you have the same amount of fluid. The second thing that we can say is, of course, if it was more dense, this will be pushing down, so the equilibrium would have found it in more. Because if you put water, what would you expect if you put water? You can do that as a sanity check. What would you expect if this was water? Well, you wouldn't know the height in here, right? But obviously the height in there would have to be the same as here, because the weight here is going to be larger, and so only when the columns match each other are going to be larger. But at that point, both have the same pressure. So obviously this is what we're saying. If we had whatever is due to this is due to that. That's what we're saying, because the pressure needs to be the same. If this was water, then the here will be there, so here and there, right? But the water in here and water in here, the pressure needs to be the same if it's in equilibrium. So these are ideas that we can use pressures to actually find out densities on liquids, right? And again, you can see while oil and the oil stands on top of the water. Oil is less dense, so for a given volume, it has a smaller mass, so it's less heavy, so to speak, so the water is going to sink in the oil. If you have something which is between oil and water in density, it's going to be in between. And that's why you can see all those displays where you have different fluids in layers, right? Provided they don't diffuse. Okay, once they diffuse, they can make compounds and things become a little more complex, but for physics 2053, it is enough. But this is, again, another idea of, oh, why do we have different heights? Because I have different weights, and those are compensating for the pressures. If this is an equilibrium, pressure needs to be stable. Same height has the same pressure, and this therefore need to be, the same. We introduce explicitly the pressure of the atmosphere, because of course it's there, but the pressure of the atmosphere is always there. So this is another of those examples where working directly with the gauge pressure would be enough to solve the problem. Problem number 6 in discussions is about the hydraulic press. We have seen the theory, let's say how we put it into action. So we have hydraulic press for compacting powder samples that has a large cylinder. We can say that the large cylinder has a diameter, well, we can say D1, it's 10 centimeters, which is 0.1 meters, and so we will use that pi times 0.1 divided by 2, because diameter is twice the radius, pi r squared is the area, which is going to be 10 to the minus 2, oh, excuse me, no, that's going to be 10 to the minus 2, 1/2, so 1/4, 0.25 or pi fourths 10 to the minus 2 meters squared. And then we know the diameter of the second piston or the cylinder is 2 centimeters, which is of course 2 10 to the minus 2, and so that's going to be 1 10 to the minus 1, so it's going to be 1, so 10 to the minus 2, excuse me, squared, and that's going to be 10 to the minus 4, right, because it's 10 to the minus 1, so 10 to the minus 1 is squared, 10 to the minus 2, and then the 1/2 is going as 1/4, and so this is going to be times pi. Okay, and the square meters, and so we have everything in square meters. So very good practice, probably always go to international units. The lever is attached to the small cylinder as shown. The sample, which is placed on the larger cylinder, has an area of 0.4 square centimeters. Oh, okay, so let's write area of the sample. It's 4 square centimeters. Now remember, the 1 meter is 10 to the 2 centimeters, which means that 10 to the minus 2 meters is 1 centimeter, right? That goes divided. So then a square of square, that's going to be that 1 centimeter square is going to be 10 to the minus 2 square meters square, and this is 10 to the minus 4. So if I want to go there, I'm going to have 4 10 to the minus 4 meters square. And that's the area of the sample. And this is what is the pressure on the sample if 320 newtons is applied on the lever. Assume the lever is moving at a constant angular velocity. Now this last sentence is just to clarify that there is no angular velocity, and so immediately we know, because there's no angular velocity, let's write it here, there's no change in angular velocity. That means that alpha is 0. And why is that important? Because then torque is going. And now we have a press. And we're going to be applying a force in here, but the force goes, let's make this a little bit larger maybe. But the force is the result of a lever where I apply a force in here. So I'm going to be pulling down here, there's going to be torque. Now I'm saying there's no torque, but there's going to be a torque, so there needs to be not net torque. That's how we're going to figure out how much of that force I'm doing here is going to be transferred in there, right? So this is me pulling down. So how can I figure that one out? This is a little bit more difficult, and it's necessary, but just to see how we can put everything together to make very complex things that when we go step by step is actually very simple. So the first idea we see is that we have a lever, so the lever is going to be pulling down. Now it's a force acting down that's going to be transferred. The axis of rotation is not in here, it's in here. So when I pull down, this is going to be pushing down the piston, right? So I can just do this and that thing pushes down. So this, it pushes down the piston. So how much force is pushing it down? This force needs to be translated there. And how do you do that? Well, first of all, you have a distance, a force acting at a distance. According to the diagram, that's 2 times L, whatever that is. And then this is L, right? The sizing there is L, the sizing there is 2L. So the net torque is going to be taking positive torque this way. That will be the force times the distance. The sum of all the torques is going to be the force times the distance, and then I have, and this is important, this is pushing down. So do I add the torque? No, because that's the lever pushing on the piston, action reaction. What the lever does on the piston does on the lever. And what I'm analyzing now is the torque. When I am applying a force in here, I have force, which is the normal force of the piston pushing up. Because this is going down, this is pushing up. Is the reaction of the piston to the thing pushing down. So the bar pushes on the piston pushes on the bar. I pull on the bar experiences a force, and that's the one where I'm doing the torque balance. So this one is generating F2L, this one over here is going to be generating a normal force times L, and that needs to be equal 0. And of course that's where I can find the normal force, because we said there's no angular acceleration, right? This is kind of in equilibrium, we're moving in constant velocity. So what we're going to find is that force 2L, it's equal to normal force times L. L's and L's cancel, and so what I observe is that the normal force actually is twice the force that I am applying. And if I am applying 320, the force that I am actually applying on the piston is going to be multiplied, and that's 640. And then we have here another example of multiplying forces. That's why a little bit more difficult, but we see it. Of course, we'll have to travel more. The circle described here is larger than the circle described here. So I have multiplied the force at the expense of having a reduced arc length of the piston. So to multiply my force, I go farther away, so I have a larger torque with the given force. It multiplies the force and the x so I go larger, so this is the axis of rotation, so this goes slightly less, so this arc is larger in here than it's in here, right? This is the piston, and this is where I am put the handle of the thing. So I need to do all this length for this one just to move here, but I'm multiplying the force, so energy gets conserved. And this force is actually the one that the piston is going to be observing, which is the one that I'm going to be using in my Pascal press. So what do I have? That the force in 1 divided by the area in 1 needs to be the force in 2 divided by the area in 2. So that means that the force that the sample experiences is going to be what? It's going to be the force that I apply, which is that force normal, that's like F1 if you wish, divided or times the area of A1 divided by the area of 2. Important though, this A2 is not just the area of the piston. Actually, it is the area of the piston. So what we're going to actually observe is that area of the piston is the one where you have the pressure because the liquid is pushing on the piston. But what they're telling us, that's over that area. What they're telling us actually is that there is a sample, and that sample doesn't have the entire area of the piston. And so the question says like, a lever, the sample which is placed on a larger cylinder has an area of 0.4. What is the pressure of the sample if 320 newtons is applied to the lever? Right, so pressure is the force divided by area. From here we can say the pressure here needs to be the pressure there because pressure it's the same across, it transfers across the fluid, right? So it's going to be transferred the pressure in here, now it's going to be distributed in a large area. And then there's another thing which is also important, is that's going to be the force on the piston, but that force is going to be applied also on the sample because that's the force going up. So that's the force that the sample is going to experience. The piston, so let's make it in here. Okay, the piston is going to be pushing up with the force 2, and it's going to be pushing on the sample. So what force does the sample experience? Force 2. But here's the thing, the question is about the pressure on the sample. So the pressure on the sample is going to be the force 2 divided by the area of the sample. So we will have to do that at the end, right? So if I want to say the pressure of the sample, that's going to be the force 2, which is F1, and then area 2 divided by area 1, which is the mechanical advantage, times, or divided by, right, that divided by the area of the sample. And now, of course, we can just write all the numbers. Now, important thing here is to realize the area A2 is the smaller piston, so actually I have swapped the notation, right? If the force 2 is the force in here, that should be area 1. So these are the ones I'm going to change to A1 and D1, and this is going to be D2 and A2, because this is, if I make the piston, that's going to be A2 and A2, and that's going to be the area A1, right? So it's important probably to make diagrams to avoid finding errors at the end, but there was an error in there. But once we've realized that, then this becomes trivial. So what we're going to observe then, if we put all the numbers, the force 1, which is the force I actually applied, is going to be 640 because I applied 320, it multiplies because of the lever mechanism, that's going to be 640, times the area 2. The area 2, it's we calculated over here, that's going to be pi fourths of 10 to the minus 2, divided by the area where I actually apply the force, which is 10 to the minus 4 pi, divided by the sample, which is 4 10 to the minus 4. So from here, we're going to find that the pi's and the pi's cancel, and so this is going to be 640 divided by 16 times 4 times, 10 to the, that's minus 8 and minus 2, so we can make it explicitly, so you see that as a sort of as practice. we're going to have 10 to the minus 2 in the numerator, and then divided by 10 to the minus 4, 10 to the minus 8. So minus 2 minus minus 8 is plus 6, and 64 divided by 16 is 4t. So that's going to be 40 divided by, times 10 to the 6, right, which is the same as 4, 10 to the 7 Pascal. So what is the pressure that the sample experiences actually? 410 to the 7. And how do we achieve that huge pressure on the sample? Think that if we were applying this force that we originally have, which was 320 newtons, 320 newtons was the original force. If we were actually applying that force directly on the sample, the pressure on the sample will be 320 newtons of that force divided by the area, which is 410 to the minus 4. And 32 divided by that is going to be 80 10 to the 4. So that will be 8 10 to the 5, which is about 2 orders of magnitude, right? It's 2 orders of magnitude, so 100, but in reality it's half, so it's 50. So we have multiplied 50 times the pressure just by using the lever, and by the lever we multiply times 2, by the pressure of the thing we multiply times 25 and 50 25, and then we have found how we can use these machines in a to our advantage, right? Because if you had to crash the sample and you only have this much force that you can make pulling down, then you would apply 10 to the 5 pascals, which is say 0.8 megapascals. But because you are oh, actually that's 100, that's no, that's 200. So that's going to be 8 times to the 5, you can divide this by this, or this by this rather, and so you're going to have 1/2 and then 100, so it's 50 times more, right? So you multiply 80, that's 6, and then 5, correct. So it's 50 times more, where twice comes from the lever, the torque, and 25 comes from the area ratio. 1/4 over the 100, yes. Anyway, the idea. We threw the torque, but forget about the torque if you want, just through the hydraulic press. This was just, like the cherry on the cake to make it even more exciting, because otherwise it's kind of boring, because this is boring. But with this we see, how we can combine things. And by using stuff like this, we're multiplying the force acting on the piston through the lever mechanism, and the second machine is the mechanical advantage due to the hydraulic press. And with that we have multiplied times 50 the force that otherwise we would be capable of doing. Now, of course, that comes with a cost, which is if you need to make 1 millimeter in here, because the force has multiplied 50, you have to move this 50 millimeters in here of arc in total. Otherwise, you wouldn't achieve that, right? Because energy needs to be conserved. So the amount of work needs to be the same. So if let's say you crash 1 millimeter, you achieve 50 times more force, then you have 50 times. You need to apply 50 times more displacement on the force where you're applying it, right? Again, work is force times displacement, so if the force is 50 times less, let's say, than here, that is also, you have to multiply that. That mechanical advantage needs to come through the displacement. You can make the numbers anyways. The idea here is just the concept. And this is just a simple application of Pascal, which again comes from all the theory we've seen, how we can put it together to analyze fluids, and analyze in Pascal principle, which is the principle of hydraulic presses.